we had a really good kind of first session with our mechanism review. And because that's not something that was recorded, and I've had this same conversation with a few students afterwards, I thought it would kind of be helpful just to put it down in a space where people who didn't get a chance to meet with me directly could kind of see. So there's two sort of big picture concepts that we talked about with students. And the first is, when you're looking at mechanisms, what you need to be able to do is identify things that are nucleophiles and things that are electrophiles. And why that is the case is when you draw arrows on your mechanisms, arrows start at nucleophiles, and that's generally going to be electrons that are in bonds or lone pairs. So that's electrons that are in bonds or lone pairs on atoms. Okay, and it's going to go to electrophiles. So arrows start at nucleophiles and go to electrophiles. And the two main electrophiles that we've seen thus far are carbonyl containing compounds. Okay, and in the next little bit here, we'll sort of explain the differences between the two classes of carbonyl containing compounds we've seen thus far. And why carbonyls are great electrophiles is if we were to draw a dipole moment, we would see that it's partially positive at that carbon atom, and this makes that a great electrophilic atom. So again, we have arrows that start at electrons that are in bonds or lone pairs on atoms, and I should highlight that those lone pairs are generally atoms such as oxygen or nitrogen, and they are going to go to atoms. Okay, and here we see one of the atoms that we often go to. It's the carbon of a carbonyl containing functional group. Another atom that we frequently can go to is a proton. Now, in our first reaction mechanism, I'm going to flip back and forth in a minute here to kind of remind you of the different mechanisms that we did. The first mechanism that we did actually was just an acid-base reaction, and that's where we had our nucleophilic amine. Let's actually flip to it right now. We had our nucleophilic amine that we had here. Wow, I am flipping all over the place here. Hang on. Too far. We had our nucleophilic amine right here. It did not come and nucleophilically attack and form a new bond there. The reality of what happened is, again, look at these arrows. After you watch this video, go back and look at whether they're your mechanisms or the keys and see that every single arrow starts at electrons, lone pairs or bonds, and goes to atoms. Okay? Now again, the atom that a lot of people maybe wanted to go to was this carbon of this carbonyl, but in this case, it goes to a hydrogen atom. Frequently, atoms or arrows come in pairs because when we draw this arrow, this shows a bond forming. Well, most things that we have in our structures are going to have complete octets already, so forming a new bond will create an octet violation unless we break a bond. So these are keys that usually for me will just be a red flag that something is wrong on a mechanism. Generally, we see two arrows, one for a bond forming and then one for a bond breaking. And those arrows are going to flow in a direction. I never see arrowheads coming together. I never see arrowheads going away from one another. So those are red flags that something maybe didn't work quite right. Okay, so coming back to this first slide here. So things that we tend to see as electrophiles, atoms, are going to be the carbon atoms of carbonyl containing functional groups, and we'll get to some more elaboration on that in a minute, and hydrogen atoms, protons. We're going to see a lot of protonation and deprotonation, some proton shuffling that we're going to do in our mechanisms, and so that's going to be something that we will often see, is that we're forming a new bond to a proton because we're deprotonating something. So just highlighting what, again, are the atoms that we're going to tend to see here. We're going to have carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, but I don't think any of our mechanisms that we're going to see in these 22 are going to have sulfur, okay? But the ones where we see lone pairs are going to be that oxygen and nitrogen. So one other thing just to highlight, and I encourage you to sooner rather than later start using these when you do your mechanisms. Rather than using water, even though you can use water as a base or an acid, use this guy, B with a dot. This is going to be what we call a general base. So this is going to be something, nucleophiles are bases, this is going to be something that can easily grab a proton, okay? And then when we have something that's going to be a general acid, we're going to see BH+, okay? So this is going to be a general acid. So that's going to be something that will be able to donate a proton. So all of this proton shuffling that we're going to start seeing in mechanisms, I want you to start thinking about using these species rather than water. Even though you can use water, and we've got lots of water, you know, biochemically, those guys are going to be more helpful. Okay, so when I was working on this in class with students, the other thing that we sort of talked about was looked at the different kinds of carbonyl-containing compounds we're going to see. And carbonyl-containing compounds generally fall in one of two classes, depending on what the identity of X is, okay? So if X is going to be a good leaving group, okay, we're going to have one kind of chemistry, and here's some examples of things that would be X as a good leaving group. You could have acyl halides, for example, something like this acyl chloride. Now, you're going to see that in organic chemistry, but you're not going to see that in biochemistry because it's just not a functional group we see biochemically, okay? Other things that you can see, and this was actually reaction mechanism 2, you can see acid anhydride. So I'm going to kind of highlight here. This was reaction mechanism 2. Okay, again, too reactive to see in biochemistry. So what we saw in reaction mechanism 3 was a good leaving group, but it was a biochemical leaving group. So this is BRM number 3. So highlighting good leaving groups are things like a chloride, a carboxylate group, an OAMP group. So why are those good leaving groups? Well, those are good leaving groups because they are weak or stable conjugate bases. Okay, so if we look at what we have here, Cl-, that is the conjugate base of a very strong acid. Carboxylate group, that is a conjugate base of a fairly strong acid, a carboxylic acid. OAMP, we really don't think of the acid part of that, but if we have a negative charge on that oxygen, it's easily stabilized by the rest of that group, okay, because there's also a phosphate group that's there. Okay, so that's going to be things that we saw in our second and our third reaction mechanisms, and I'll flip through those in just a second. Those were good leaving groups, okay? I'm going to actually start another page here just to kind of highlight the kinds of chemistry that's going to happen when we have something with a good leaving group. So when X equals a good leaving group, here's the chemistry that we're going to see. We're going to see nucleophilic attack on our carbonyl carbon.
I don't know what that means. If you like, I can search the web for.
No.
We're going to see nucleophilic attack on our carbonyl carbon.
No, Siri. All right, sorry. Nucleophilic attack, and that forms a tetrahedral intermediate. Okay, so I'm going to flip to a couple mechanisms to sort of show you this. When we have the ability to do some proton reshuffling, okay, that's going to change who the good leaving group is. So that's the key here. When we do proton reshuffling, we change who is the good leaving group. If you want to make something be a good leaving group, you want to protonate it. So good leaving groups are protonated, okay? We do a little bit of proton reshuffling, then we're going to decompose our tetrahedral intermediate, and that is going to reform our carbonyl. So we're going to reform our carbonyl, and what we really have then is we're going to have this guy, when we add a nucleophile, what we get at the end is we do a substitution. Our nucleophile is going to be in that position, and then our leaving group has left, okay? So that's one kind of chemistry that we see. We see that in reaction mechanisms 2 and 3. Okay, so let's actually take a second and we'll show that, right? So here's reaction mechanism 2. This is where we've got our good leaving group here. So that's our good leaving group. We've got nucleophilic attack. Okay, nucleophilic attack. We form a tetrahedral intermediate. Okay, we do some proton reshuffling. So that's our proton reshuffling because we want to change who the best leaving group is. Right now, this guy's the best leaving group. Then we decompose our tetrahedral intermediate. We're reforming that carbonyl. And that good leaving group leaves, and we have substituted in our nucleophile there. Okay, so that's how that chemistry works. And reaction mechanism 3 was basically the same thing, except we have a biologically available good leaving group that's right there. Okay, so that's going to be the theme you see when we have a good leaving group. Okay, so highlighting some things that you might see where X is a good leaving group. We saw reaction mechanisms that we've already seen, but maybe you could have things like amides and esters as well. We're going to see those mechanisms a little bit later. Okay, the last little piece is to highlight, well, what if X is not a good leaving group? And basically that's going to be when X is either hydrogen, when we have aldehydes, or an R group, a carbon atom, when we have ketones. And so when X is not a good leaving group, again being hydrogen or an alkyl group, here's kind of what we see. And that's what reaction mechanisms 4, 5, 6, and 7 were all about. So let's come over here and let's draw those parallels. So when we've got our X group is equal to not a good leaving group. Okay, and let's kind of highlight and keep our kind of color scheme going here that this was a good leaving group. Okay, so what's going to happen now is we're still going to have nucleophilic attack. I should have put nucleophilic attack there. So nucleophilic attack is still the first step. We still form a tetrahedral intermediate. We're still going to do proton reshuffling. And here's where things become different, because even though the purpose of that proton reshuffling is to change or eliminate.
Okay, I found this one.
Our good leaving group. What am I saying that they really like there? Okay, once we do that proton reshuffling, then we are going to be done. We cannot decompose that tetrahedral intermediate because there is not a good leaving group. And so we are done, and we are done with a tetrahedral intermediate. It's not really even an intermediate, it's a tetrahedral product. So let's look at those reaction mechanisms here. So that's going to be reaction mechanisms 4, 5, 6, and 7. So if we look at 4 here, okay, so now that's not a good leaving group. Okay, but we still see the same steps: initial nucleophilic attack. Oops, I don't want that. Nucleophilic attack. Okay, those electrons move. Notice how, looking here, I'm seeing like 2 sets of arrows. I always see arrows in pairs, arrows in pairs, arrows in pairs. Arrows start at electrons, bonds or lone pairs, and they go to atoms. You will always see that, and that's again how I very quickly can tell if there's something that's not right with a mechanism. So nucleophilic attack, form a tetrahedral intermediate. So here's our tetrahedral intermediate. We're going to do some proton reshuffling. Proton reshuffling makes this guy no longer be a good leaving group, so highlighting this is actually a good leaving group right here. If we decompose this tetrahedral intermediate, we would have this guy leave as a good leaving group, but that just gets us back to the beginning. That doesn't move the mechanism forward, okay? So we do some proton reshuffling, we get to this guy, and again, there's no good leaving group if we were to decompose that tetrahedral intermediate, other than kind of if that guy was protonated, we'd go back to the beginning, and that's not a forward-moving reaction mechanism. Okay, so that's what we have when we don't have a good leaving group, and this forms what we call a hemiketal. Now, reaction mechanism 5 was pretty easy because all you had to do was swap out that bad leaving group that was a carbon for a bad leaving group that was a hydrogen. Mechanism looks exactly the same. Okay? Now, a little bit different when we get to reaction mechanism 6, because it's like, you know what? Let me add some more alcohol here. But you know what we have here, and a lot of students when they do this, what they'll want to do, or they are want to do, is say, let me just have this guy come in. I'll do a substitution reaction. I'll just do nucleophilic substitution. This alcohol is going to come in, and then this guy is going to leave. Too sterically hindered, okay? And we also are not going to do an SN1 reaction because we don't have carbocations that we see in biochemistry. So here's what happens. So 6 and 7 are a little bit different, but they sort of follow the same sort of theme here. We want to make this guy leave. Okay, protonate him. Protonation makes things more likely to leave. Now we're going to have this guy facilitate that departure. A lot of times people just want to have a single arrow here and be left with a carbocation. If you're drawing a carbocation in one of my mechanisms, it's not correct. Now, you could think about this departing, leaving this positive charge, and then we stabilize that positive charge by having those electrons slide down so we don't have an incomplete octet on carbon. That's a possibility, but it's easier just to envision this happening in a concerted or one-step process where we've protonated our leaving group to make it a better leaving group, and then we're going to have the reformation of our carbonyl that we have there. Okay, notice that this is not something that we can kind of deprotonate and maintain that carbonyl. Okay, but what's really nice about this species, not only have we eliminated that guy and we've opened up space to have something else come in, we've made this very electrophilic because this positive charge on that oxygen makes that carbonyl carbon even more electrophilic. So nucleophilic attack here is going to look very similar to things we've seen before. Generate a tetrahedral intermediate, do some proton reshuffling. Really here it's just a deprotonation of our incoming nucleophile so that we can make sure that we don't go backwards and lose it. Okay, and then we get to our final product here, which is a ketal. Okay, so one of the things that we're going to kind of translate this onto, and just to give you a preview here, sugars. We're going to get to sugars in a little bit. Sugars have a carbonyl containing functional group on the end of a sugar, and then a whole bunch of alcohol groups throughout the sugar, and then there's one on the end. That alcohol group and that carbonyl containing functional group are what we use to form a hemiacetal or a hemiketal that cyclizes sugars. Now, when we want to polymerize sugars, that's where we have our cyclized sugar, and then we have another alcohol group from another cyclized sugar that comes in to do this chemistry. Okay, when we have our second alcohol that comes in here, it's a cyclized sugar that comes in, and that's how we link sugars together. So that's the biochemical connection. I know sometimes people, when they were writing sort of the descriptive part, I don't need you to describe in words what's happening with the mechanism. What I want you to do is think about the biological or biochemical significance or application. That's this part that's down here. So if you're ever looking at the keys, that's what I want you to be able to put in your own words and write down. Why is this important? Why did Dr. Parenti have me learn this mechanism? Where am I going to see it again? All right, hope that helps to kind of give you more of a big picture of how to think about mechanisms.